Hello everyone, welcome to the power system class. Today we're going to talk about introduction to power systems and complex algebra. My goal is for this class to not to talk about power system introduction. I'm going to talk about complex algebra because this is very important for this power system, how to manipulate complex algebra. So let's go back to that complex algebra part of this class right here. So you have seen this before, how to manipulate a complex algebra in high school or in your calculus class or in your easier 240. So let's see if we have zx plus iy, I is your complex algebra, right? But in power system, we replace I with j. So I'm gonna give you that thing over here. In power system, we replace I with j because I represent current. And this is basically negative square root of -1, right? You all know that. So magnitude of this complex number over here would be x squared plus y squared. And the angle for this complex number here would be tan inverse y over x. You all know that. So we're gonna just start from the beginning. Then let's see where else we can go with this. Right here. So I have two complex number, z1 and z2. This complex number, they're in a Cartesian representation right now. We can represent them into polar form, like we can say that g1 magnitude and angle. We can represent like that, and this one could be represented at, you know that a complex number could be represented like 5-6 different forms. This is one of the forms. So we know how to find the magnitude, we know how to find the angle from the previous slide. So for here, if I try to find the magnitude of this one, that magnitude would be 39.05. Angle would be negative 50.19 degree. And for this one over here, the magnitude would be 18.86 and your angle would be 57.99 degree. So we try to add or subtract these two complex number. Addition and subtraction is easier to do in Cartesian form. So it would be like 25 negative j. You can see that I replace I with j for our power system application. Then tan would be plus j 16. Then if you add them, you will get 35. All right, and you will get negative j 14. Then if you subtract them, you'll get 15. Then if you subtract, you get 46, negative j 46, right? So that is addition and subtraction, and very easy to do it in Cartesian form. But if you want to multiply them, multiplying in a Cartesian form is not easy. So we should do them in a polar form. So we can use this two polar format over here. If you now multiply them, your multiplication should be multiplying this to magnitude here. That will give you 736.8. And when you're multiplying angle, you're basically adding them together. If you add them together, one is positive, one is negative, so you're going to subtract from each other. You're going to get 7.80 degree. All right. When you divided them, you divide the magnitude separately, so that will give you 2.07 here, 39.05 divided by 18.86. Then when you're dividing your angle would be subtracted from each other. So if you subtract from each other, basically adding them together, because negative 50.19 minus negative 57.99 will give you negative 108.18 degree. So this is a very quick manipulation of complex algebra. So let's move forward here to relate them into our power system. So complex algebra in power system. In a time domain, this is the time domain over here. All right, it's a time domain. So when you use in time domain, you can easily go from time domain to frequency domain and back and forth if you know the frequency. So from time domain, this is the time domain over here. This is the phasor domain. So you can see that your angle is 0 because there is only when time is 0, your angle is 0 here too. So there is no reference angle. So that's why time is 0. And these two magnitude, this is the magnitude, this one is called RMS. So time domain to phasor domain, you need to use RMS value for the phasor domain. All right. So this one has a positive negative theta 0 degree because this one has a reference angle here, theta. All right. So now how does it come together in your actual signal? So let's take actual signal. Let's say that your time domain signal is 170 cosine omega t. That's your time domain electrical signal. So if I go into phasor domain, I need the RMS value for this one. The RMS value for sinusoidal signal is the peak value divided by square root of 2. So VRMS over here would be 170 over square root of 2. That should be giving you 120. Right? So now, if we're trying to find the phasor domain value over here, that would be V. So it is 120, and there's no reference angle here. There should be 0 degree. Right? So now if I go into, let's say, another signal I have like this. Let's say I have 170 again, same, sorry, no, there's no angle here. 170 cosine omega t plus 30 degree. So then in the phasor domain, I will have, sometime in your phasor domain, you can use this bar here, or you can just leave it like that. Then you have 120 now, you have a reference angle now, which is 30 degree. So that's how you go back and forth from time domain to phasor domain. So if you want to go back to the time domain again, you have to make this 120 times square root of 2, that will be 170. Then if you know the frequency, that's omega t here, plus 30, right? So now see that you have a Z angle, Z here, impedance over here. Let's make your impedance a little bit simpler impedance here. Let's take a value that is kind of easy to do. Let's say it's 10 plus J10. Let's take the 10 plus J10 ohm, right? So this is all voltage. Don't miss your angle voltage over here, unit. All right. So that is basically, if you go into polar form over here, 14.14 angle would be 45 degree ohm, right? So now if I try to find I over here, so I would be V over Z, right? So now you have 120, let's use 0, 1, so it will be easier, over 14.45 degree. So your I would be, you'll get 8.48, and it will be negative 45 degree amps. So this is your in phasor domain current. If you want the time domain current over here, so I have to multiply this one by square root of 2. So if I do that, let me get a calculator here. If I do that, 8.48 times square root of 2 will give you 12 here. I have 12. Let's see, did I make a mistake here? 120 over 14.14. Yeah, fine. So it's 12. And cosine omega t, there's an angle here, negative 45 degree amps. So this is the time domain current in your circuit. So you can see that how your phasor domain and time domain can be interchangeable, right? So these are both here. So this is the time domain. This is your phasor domain, right? So all the calculation in your power system class, we always do them in the phasor domain. Basically, you see that how easy to do the calculation in phasor domain. Then after the calculation is done, we can convert it to the time domain as soon as you, as long as you know the frequency and angle comes from the calculation over here. All right. So we're going to talk about this in the class. We're going to also talk about it in the class. All right, we're going to talk all of this in the class. So that's all for today class. This class goal was today was to basically refresh your complex algebra and connect that into power system using time domain and phasor domain. Hopefully you all got the idea and understood the concept. See you guys in the next class.